Moving on to week 4. So today we'll be talking about 4.1, which is the idea of a lot of definitions, essentially, about linear independence, basis, dimensions, span, spaces. It's just a lot of ideas that will kind of be thrown at you that we'll use in a bit, now/later. But I think it's a little bit overwhelming because it's a lot of like vocab. So let's get started. So 4.1. We introduced the idea of linear independence versus dependence. So like we talked about in 1.1, linear things are like systems of linear equations are when you combine variables and constants linearly, which literally just means plus and minus. Like linear is not, it's just like not multiplication in the context of what we're talking about. So linear combinations is the idea of how we can take things and combine them by adding and subtracting them and multiplying by some values, some scalars to scale them up or down, but like combining them in that way, which I feel like is most commonly described as like C1, V1 plus C2, V2, etc., where C1, C2, all the C's are real numbers, and then V1, V2 are like vectors, so like R3, for example. When we have linear combinations, that is just like when we take that and then combine them, that means that we can make a new thing. So it's always going to be the thing that we make when we add things together, when we combine them, is always going to be of the same form as like V1 and V2. Like if I linearly combine two 3x1 vectors, I'm going to get a 3x1 vector. That resultant 3x1 vector is linearly dependent on the other vectors because it depends on those vectors to be made. It is related to them by some linear combination. So we can combine some scalars and some vectors in some way to get them to get each other. Linear independence, so this is linear dependence versus linear independence, is when we have vectors or polynomials or something like that. Again, it's the broad idea of it, and you can't combine them to get each other. So there's no way for us to do C1, V1 plus C2, V2, blah, 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 to get them to be each other. They just exist in different facets of the certain space. Like they can't be made from each other. So linear independence is when a set of vectors, so that none of them can be written as a linear combination of each other, except again for the trivial solution. So obviously for, let's say we have 3x1 vectors. So looking at, for example, like this one, this is a linearly independent example, spoiler alert. So we can combine, there's no way for us to like get any of them to exist like this. Like I can't add any of the two to get the third. I can't subtract. There's no way to do this. Obviously, there always is the nuclear option. Just make everything 0. So that's what we refer to as trivial solution again. So when we say something's linearly independent, it's when there's no solution besides the trivial solution. Then the idea of a span is, so span I like to think of as a noun and a verb. So for span is, as a noun, it's the space that can be generated by some vectors, and then span as a verb is making that space. So as a noun, when you think about the vector space that we talked about before, so most of the common ones are like R3, R2, those things. The span of R2 is R2. Like, it literally means what it means in like normal English, is it spans all of these things. It can make it exist in all of these things. And then as a verb, it's that certain vectors span R3. So like in this example, these vectors span R3 because it can make every single vector in R3. So thinking about more, I guess more common is like thinking about getting ahead of myself, but the standard basis for R3. So these are the standard basis of R3, where just think that these 3 things, you can linearly combine them some way, C1, C2, C3, to make every single vector in R3. Like literally every single one, right? Because you can just change whatever C1 is to scale it in the X direction. You can change C2 to scale it in the Y direction. You can change C3 to scale it in the Z direction. So these 3 vectors span R3. And the span of these vectors is R3. So it can be used as a verb or a noun. Then we get to the idea of basis. So a basis, very big idea. We'll talk about it a lot. So a basis is a set of vectors, polynomials, matrices. You get the gist. When we say vectors, we don't just mean literal column vectors. They are the set of vectors that are linearly independent. They must be linearly independent, so they cannot be made from combinations of each other, and they must span the vector space. So they must be able to make every single thing in there with the linear combination. So for R3, I need to be able to make every single thing in R3 with these elements. They also must be a minimally spanning set. So like, kind of like Goldilocks. Like you can't have too few things, because if you do, then you won't be able to make everything, right? Like if I only have two vectors, if I only had these two, if I only had 1, 0, 0, 0, 1, 0, I couldn't make anything in the z direction. That would be completely missing. So I need to have the not too little, and I can't have too much. So minimally spanning means if I remove one vector, any vector, it will no longer span. So we can't have too much too. We don't want redundancy. Inherently, if it's linearly independent, they won't be redundant, but we call it minimally spanning. This brings us to the idea of standard bases. So every vector space, R3, R2, P3, R2 by 2, so many things, all of them. There's infinitely many bases for these vector spaces, because as you can imagine, there's infinitely many vectors that are linearly independent that span the space. Because you could just say, okay, I've got my standard basis, which makes sense. Like I've got 0, 1, 0, 0, 1, 0, 0, 0, 0, 1. Cool. But also, what if I just made this a 5? What if I made this a 2? I made this a 3. Technically, this set still generates the exact same as this one. Because then I can still just scale these three vectors, these three scalars, however I want, however I need to. So there's infinitely many bases for a given vector space. But there are some standard bases that we can refer to. So here are a few of them. So for R2, this is the standard basis. So it makes sense. Like standard bases are what you would imagine would be them. It's just like 1, 0, 0, 1. And then for R3, we've got 1, 0, 0, 0, 1, 0, 0, 0, 1, as I've talked about before. For the polynomial spaces, so P3 is the space of all polynomials up to degree 3. Its standard basis is this. So if it's up to third degree polynomial, we're going to need, if we want a number, so that 1, if we want an x, then an x, and then an x squared and an x cubed. So every polynomial up to degree 3, I can choose to use this. I can choose to use this one. I can choose to use x. I can choose to use x squared, and I can move this. I can choose to use x3. I can linearly combine these 4 things to get whatever polynomial I want. And then R2 by 2 is a common space where it's just the set of 2 by 2 real matrices. So imagine it like we just put a 1 in every single spot, and then we could obviously make every single possible R2 by 2 matrix using these. Every minimally spanning basis for a vector space has the same number of vectors in the basis. So, right, we have infinitely many, but every single basis for R2 is going to have 2 things in it. Every single basis for R3 is going to have 3 things in it. Every single basis for P3 is going to have 4 things in it. Every single basis for R2 by 2 is going to have 4 things in it. Because a basis cannot have linearly independent components. So whatever you're going to use, you're going to need, right? So for R2, you're always going to need 2 by 1 linearly independent vectors. For R3, you always need 3 by 1 linearly independent vectors. This conserved value is called the dimension, where it's the common number of vectors in vector space in a basis. So the dimension of R2 is 2 because there's 2 things in every single basis for it. For the polynomial spaces, it's always the degree plus 1 because we have to count for that scalar, that 1 that we potentially would use. And then for Rn, it's always just going to be, the dimension is going to be n. So lots of definitions. Let's talk about linearly independence. So you're going to be asked a lot if some vectors are linearly independent or not. So how can we figure that out? We want to see, is there some way to linearly combine them? So for this example, we want to see, is there a solution to the linear combination, right? Is there a way to make them linearly depend on each other? So one way we can write this is like this. So I want to see, the order that I put these in don't matter, just because like I could just as easily put this vector here, so on and so forth. I want to see, is there a way to make this true? So the way I can rewrite this is, if I just move everything to the left-hand side. Right, like this is essentially what we're solving. Like, can we find C1, C2, C3 so that this can be true? Yes or no? This is a system of linear equations. We talked about how matrices can be valuable for that back in 2.1. So let's make them useful. So I can just make the coefficient system 2, 3, 2. C1, C2, C3 equal to 0, 0, 0. Boom. What? So now I can solve for this and figure out, is there a solution to C1, C2, C3 such that this is true? And again, here we're not looking for like infinitely many, or I guess we can't look for infinitely many. But here we're trying to see yes or no. Is there a solution or is there not a solution? So we can do that by going reduced row echelon form, solving for the reduced row echelon form of this augmented system. So -3, 2, -3, 1, -1, 3, -2, 3, -2. Augment that with the 0 vector, do the reduced row echelon form. If I do the reduced row echelon form for that, I get 1, 0, 0, 0, 1, 0, 0, 0, 1. This tells me that the only solution, that it's unique. It's unique because it's the identity matrix. There's only pivot variables. Same thing we talked about in 2.1. But the unique solution is C1 equals 0, C2 equals 0, C3 equals 0, which is, if you remember, the trivial solution. Something is linearly independent when it cannot be written, so there's no solution except the trivial solution. So in this case, we're like, oh, there's a unique trivial solution. So it is linearly independent. Because there's only the trivial solution. Cool. Then if we do for the same thing for the second set, you can imagine this one's gonna be linearly dependent. We can do the same thing. So I'm just gonna sneak ahead and just write it as a matrix. So -2, nope, already wrong. 4, -4, 5, 3, 2, -4, -1, -6, 9. And I go C1, C2, C3. We want to see, is there some solution, C1, C2, C3, not the trivial solution, that makes this true? And I can do the reduced row echelon form. And then I get 1, 0, 1, 0, 1, -1, 0, 0, 0. So looking at this, I have infinitely many solutions. I have infinitely many solutions because I have a free variable. My C3 is a free variable because it doesn't have that leading 1 in it. And I don't have no solutions because I don't have any weird rows where 0 is set equal to something like non-zero. So here, infinitely many solutions. We have the relationship that C1 plus C3 is equal to 0 and C2 is equal to C3 pretty much. So any combination where we have this, I can even simplify this further. So C1 is equal to -C3. Any combination like that is going to solve the system. It's going to make them linearly dependent. So we can test that out. We don't have to, but that's the idea of linear dependence versus linear dependence. So we can do that by solving for whether or not the reduced row echelon form is the identity matrix. In this class, you could also be asked to do this for not things that will be a square matrix. So in this case, like let's say you had 3 like 5 by 1 vectors. So like 5, 2, 6, 3, 1, -2, 3, 0, 4, 5, 6, -1, 0. Sure, whatever. You could be asked, is this linearly independent or not? You will do the same thing. You'll put them in column-wise. You'll do the reduced or echelon form, and you will see, is there a solution? Is there a unique solution besides the trivial solution, or is there infinitely many solutions? That's going to be your options. Because if it's, you're not going to have no solution, because that's not like what you're kind of looking for, I guess. You'll have whether or not there's infinitely many solutions, it's indicating that there is dependence, or you'll have linear independence because we'll have the pseudo identity matrix. So if it looks like this, where you have, because you're setting all these equal to 0, like this. This means that it's linearly independent because it has the rank is equal to the number of variables. We don't have any free variables. We only have the trivial solution. Or you could have something like -2, -3, something like that. I don't know. That would make certain them free variables, and we would have that there is a combination, therefore they're linearly dependent. So that's how you can check linear independence versus dependence. All right, worksheet questions. Let A be an n by n matrix with a determinant of 3. What is the determinant of 2? There's these 2 review questions for this worksheet. I don't know why. Whatever. Okay. What is determinant of -2a, n by n? We remember that the determinant of a, when we multiply it by we multiply c times a, the determinant of a becomes c to the n times the determinant of a. So in this case, the determinant of a is 3. Oh, nope. The determinant of a is 3. And then we're doing -2 times the whole thing. So -2 to the n times the determinant of a. So -2 to the n times 3. That's all we can solve. Recognizing vector spaces. Is this a vector space? The set of rank 1 3 by 3 matrices together with the vector 0 matrix. So remember, we have our 3 things. We have closed under addition. I'm just going to write them as addition, scalar multiplication, and the 0 vector. They want us to not be able to discount it immediately as the 0 vector because they told us that it also has the 0 matrix. So they're like doing a cop out, I would say, where, okay, we have also the 0 matrix. So the 0 matrix for 3 by 3 just looks like this. And they're telling us it's there. So we have, this is true. Now we need to ask if we scale any rank 1 matrix by any scalar, it's going to still be a rank 1 matrix, right? It's not going to increase rank and it's not going to decrease rank. So it's closed under scalar multiplication. However, if we add any 2 rank 1 3 by 3 matrices, it's not necessarily going to be a rank 1 3 by 1 matrix, because you're having rank 1 does not mean that that non-zero row is the first row. So you could have like this be a matrix, and then you could also have like this be a matrix. These are both rank 1 3 by 3 matrices. If I add them together, it's not going to be a rank 1 matrix. So yes, this is not a vector space. Not a vector space. Okay, now talking about more about what 4.1 is about. Those were kind of reviewed for some reason. Linear independence in bases. Let V be the space of homogeneous quadratic polynomials in 2 variables. So any quadratic that looks like this, where we got x and y, so we got x squared, xy, y squared. First question. Are the elements x squared, xy, and y squared linearly independent? I didn't say this one. Fine. You can just say yes. Like essentially, like this one is just like obviously yes. Because there's no way to linearly, again, the keyword here is linearly combine x and y, xy and y squared to get x squared. There's no way, like, I guess I can write these out, like x squared, c1 x squared plus c2 xy equals c3 y squared. There's no way to make this true with numbers. With variables, sure, there's probably a way. But that's not the idea of linear independence. So they are linearly independent. What about x squared plus xy plus y squared, x squared plus y squared? Well, okay. Well, obviously no, right? Because I can take the first two, I can take this plus this, and that equals this. These ones are very obvious questions. This one, however, x squared plus xy, x squared plus y squared. Like, it is linearly independent, but we can kind of prove it by showing, like, if we have each of those things, where I'm going to say this is first thing, second thing, third thing. So I'm going to use the looking of them. I've got x squared, xy, and y squared. For x squared, that's just itself. For x squared plus xy, I've got those two values. And then for x squared plus xy plus y squared, I've got all three. I want to see, is there any way for me to combine them to get each other? Reduce row echelon form is going to be the identity matrix. So the answer is no, right? They're linearly independent because there's no way to get them from each other. So then the question is, what is the dimension of this vector space? It's saying how many elements are in every single basis for this vector space. So this is a basis, and this is a basis. They're both valid bases for this space V. They both have three things in them. So the dimension of V is 3. Moving on to question 4. About subspaces. Again, subspace, vector space, same difference. V is the homogeneous quadratic polynomials that we discussed earlier. Consider the subset of V that consists of the functions such that f1 of 1 is 0. So we have all of these functions, ax squared plus bxy plus cy squared, but it also always has that f of 1 is equal to 0. So let's just take that with a grain of salt. Prove that W is either or is yes or no a vector space. If it's a subspace, then complete parts B and C. What you want to see is it closed under addition, scalar multiplication, and contain the 0 vector. It obviously contains a 0 vector because every single time you plug, it has where f of xy is equal to 0. So it has the 0 vector in it. Closed under scalar multiplication. If I multiply any function that looks like this by a scalar, I'm still going to get 0. Like, no matter what, that property is still going to hold. Now I'll close under addition. If I have two things like this, so f of 1 is equal to 0, f of g1 is equal to 0, g of 1 is equal to 0. I can even show this as what happens here. So when this is true, when everything is 1, so that means a plus b plus c is equal to 0. Then let's say, I guess, let me call them. Let me write this. F of xy equal to f1 x squared plus f2 xy plus f3 y squared. So when this is true, 0 is f1 plus f2 plus f3. Then for g of xy is equal to g1 x squared plus g2 xy plus g3 y squared. That means that 0 is equal to g1 plus g2 plus g3. This is asking if I added them together, this is still going to be true. So f plus g of xy, that would mean going like f1 plus g1 x squared plus f2 plus g2 xy plus f3 plus g3 y squared. I can then pull all of them out, and then we know that where property is if we set it, if all of these equal to 0. So this is, we're set equal to 1, so this is 1, this is 1, and this is 1. And then we can rearrange, obviously, so that f1 plus f2 plus f3 plus g1 plus g2 plus g3, 0 plus 0. Close under addition. So this is a vector space. Find a basis of W. So we want to find a set of vectors, a set of polynomials such that it obeys this property. The property is that a plus b plus c is equal to 0. That's what's going to combine with our term. So we just need to find a way to define this as a set. So here, this is all we know. I'm going to say that a is equal to negative b minus c, and then I'm going to form the basis for this, like a solution set. So a plus b, a, b, and c, and I've got b, because b can be anything. I've got c, and c can be anything. I had 2 free variables and 1 pivot variable. So in this case, a is equal to negative b, negative c, b is equal to itself, and c is also equal to itself. So this forms a basis for these polynomials. So this is like a vector. We need it to be polynomials. We're talking about polynomials. So in this case, we have, this is x squared, xy, and this is y squared, because essentially we're using vectors here to help index our polynomials, because it's kind of hard to do all this. Like, we're using vectors because they're like matrices and vectors are helpful tools. So now I need to rewrite this as a basis using polynomials. We're talking about polynomial spaces. So it's going to look like negative x squared plus xy, and then negative x squared plus y squared. That's the basis that we made. And lastly, what is the dimension of W? Dimension of W is how many things are in the basis for W. So the dimension of W is 2. Okay, so that is all of 4.1. Again, it's kind of just about linear independence, the idea of vector spaces, how linear independence and dimension and basis interface with vector spaces. Very important intersection between the two things, and getting used to that. So not too bad, but 4.2 is pretty bad. People hate 4.2, so we'll get through that together. But this is 4.1.